Hello everyone, welcome to the section 8.1 notes where we're going to introduce the ideas of sequences and summation notation. And sometimes instead of summation notation, which we are going to talk about that, but there's a topic here which is called series. And series uses most of the time summation notation. But we will see here coming up the difference between sequences and series. They're very closely related. But anyways, let's just jump right into it. Right here, we're going to start with a sequence. We're supposed to write the first four terms of the sequence whose nth term, also sometimes can be called general term, is a sub n, or else you can call it an, equals 3n plus 2. And this one, we also have a name for this type of formula for a sequence, which is called the explicit formula. And the explicit formula is very similar to functions, where we even could write this as a of n, as though we're going to plug in as the independent variable into a function called a, and then that's going 3n plus 2. And so if we want to find the first term, which we want the first four terms, then we should plug in 1, 2, 3, and 4 for n. And these types of numbers, which are natural numbers, these are the domain of any kind of sequences like this. Whenever you write a sequence as a function, you can understand that the only numbers that you should plug in are these kinds of positive whole numbers. In general, that's what we're talking about. So natural numbers go in there. And if we try plugging in 1, it's going to go 3 times 1 plus 2, which is 3 plus 2, which is 5. And then the next one, when we plug in 2, it's going to go 6 plus 2 is 8. And then when we plug in 3, it's going to go into there with 3. It's going to go 3 times 3 is 9, plus 2 is 11. And then the fourth term, when we plug in 4, 3 times 4 is 12, plus 2 more makes 14. And so that's the first four terms of this sequence. Now the next sequence that we have, a lot of times you'll see in sequences this term right here that goes -1 to the n. And you can understand what's going on with this one. When n is something that's an odd number, say for the first term when we find a1, we're plugging in 1 for n, so it's going to go -1 to the first power, which this will be -1, so it's just going to go -1 times of 1 plus 3, which is -4. And I don't really need these parentheses. I would just write it again, -4. That's a sub 1. But then let's see what happens on a sub 2, because that's going to go -1 squared. Now n is a 2 times of 2 plus 3. So this is going to be 5. But then whenever you square -1, that's just +1. So it's just 1 times 5, which is 5. So the sign switches from negative to positive. And then on a sub 3, -1 cubed, that's going to be negative again. That's -1 times 3 plus 3. So we're going to get -6. And then whenever a is 4, we're going to an even power again. It's going to go -1 to the fourth power, which is +1 times 4 plus 3. So we're going to get +7. And when the sign alternates on a sequence like this, we call it, you might be able to guess it, an alternating sequence. And these come up all the time in different types of applications. But now, recall that I just brought up a second ago the explicit formula for a sequence. Right here we're going to see the other type of formula, which is called a recursive formula. And we're being given the sequence as a recursive formula. Notice how this differs from the explicit formula. It's not possible here to plug in and actually figure out what the term is. Say if we just want to jump in and find out a sub 4, which we want the first four terms. Here we have to actually find them in order though, because on this previous problem, it would have been possible to find a sub 4 without finding the previous terms. We can just jump in here with 4, plug in 4 for n, we get +7. The problem with this recursive formula down here is that when we plug in n equals 4, there goes the 4 there. A 4 also belongs there, so it's going to go 2 times a sub 4 minus 1, and then plus 3. And now 4 minus 1 is 3, so it's 2 times of a sub 3 plus 3. But we don't actually know what a sub 3 is, so we have to find that. And what is a sub 3? Well, similarly, it's going to be 2 times of a sub 2 plus 3. Now what is a sub 2? We gotta find that one, and it's gonna be 2 times of a sub 1 plus 3. Luckily now we actually do have a sub 1, and that's a characteristic of the recursive formula, is that it will always give you a starting place. Otherwise, you're gonna be out of luck. And so our starting place is 4. We go in here with 4, and it's going to go 2 times 4 is 8, plus 3 more is 11. So a sub 2 is 11, so this is going to be 22 plus 3, which is 25. And then that means that a sub 4 over here is going to be 2 times 25 plus 3, which is 53. So we get all the first 4 terms go 4, 11, 25, and then 53. And there's another bit of notation that we can expect to find in sequences, which appears in this problem right here. This little symbol, in factorial. It goes in factorial like this. That's how you pronounce it, with the exclamation mark. And what it means is you multiply all the numbers, all the integers, counting down from in until you get to 1. So it goes in times whatever is 1 less than in times 2 less than in. And then it's going to go down all the way until you get to 3 times 2 times 1. That is in factorial. And we have to define a couple that won't make sense with this notation. For example, what should be 1 factorial? We're already on 1, and so it would just, this one actually just goes 1. But then what about 0 factorial? This has a definition too, which is that even though we can't start here with 0 and then count down, and also 0 is already out of bounds on this side, we just define this one as being 1. And it makes all the formulas where we use factorial, it makes them just work out. We need that 0 factorial is 1. But this term, we're trying to find the first 4 terms of this sequence. It's going in squared over in factorial. So we'll have 1 squared over 1 factorial is the first term, 2 squared over 2 factorial, 3 squared over 3 factorial, and then 4 squared over 4 factorial. And if we calculate these a little bit more carefully, 1 squared and 1 factorial, they're both just 1, so 1 over 1, which is 1. 2 squared is 4, and then 2 factorial is 2 times 1, so it's 4 divided by 2, which is 2. 3 squared is 9. 3 factorial is 3 times 2 times 1. I may just stop writing the ones because times 1 doesn't do anything. It's really the meat of it is 3 times 2, which is 6, so it becomes 9/6, which is the same thing as 3/2. And then 4 squared over 4 factorial, that goes 16 over 4 times 3 times 2, then times 1. 6 from 3 times 2 times 4 makes 24 on bottom, so 16 over 24. And then that's going to give us, well, that's the same thing as 2/3, because they're both divisible by 8. And 8 goes into them 2 and 3 times respectively. So we get 2/3. Now we've finished talking about sequences. The next thing is series, and this is where the real applications come in, is whenever we would like to add up all of the terms of a sequence and find that sum. And that's why we use this symbol over here, which is the capital letter sigma. I'll write it like this because it's a capital one. And then that's the same S that's in sum. So we make a sum using sigma. And what this means is that we're going to take all of the terms of this sequence, which I'm going to call this the sequence AK, which goes k times k plus 4. And it's telling us which terms to add up. We're adding up here from this, which the k is the index. I mean to refer to the k as the index. And then this 1 right there, that's the lower limit, and the 5 up here is the upper limit for the index. So we should count up from 1 to 5 for these ones, and we're looking for essentially A1 plus A2 plus up until A5. And A1 is going to go 1 times 5, which is 5. A2 is going 2 times 6, which is 12. A3 is 3 times 7, which is, oh, that's 21. And I want to actually pull up the calculator here very shortly and see about finding this sum in the calculator. But let's just finish this one out. 4 times 8 makes 32, and then 5 times 9 is 45. So now we should add these all up. These make 50 together, and then that's another 53. So 103 plus 12 is 115. And that's the sum. And then there's another sum coming up right here. This sum, it does look a little bit strange. It's still the exact same thing that we dealt with before. It's just that we're adding up the number 11. That's the sequence. It's a pretty basic sequence. It just goes 11. It doesn't matter what k is, so A1 is 11. A2 is 11. Every single A going down the line up until AN, whatever the n is going to be 11. So when we add up from I equals 5 to 9, which here this index, the particular letter that's used for the index does not matter. It doesn't matter index, I will say the letter. Which letter you choose to use for the index. It doesn't matter as long as you use that same letter as the independent variable in your sequence. Which that's what it's doing right here. It's just that this sequence doesn't actually depend on anything. It's always 11. But we should expect to actually, instead of AK, let's scribble that one out. I want to call it AI. It's more like that one. And so we're adding up 11. This was A5 because see we're starting I on 5, so we want A5 plus A6 up until A9. And so how many of those should there be? There's A6, 7, 8, and then 9. So that's all 5 of these, and it makes 55. And speaking of that one, I want to take this opportunity, since this is the last one we're going to calculate, I think it is, that we can see how to do this in the calculator. So I want to go to this math button over here, math, and then I'm going to hit the number 0, or else you can scroll it around 0, the summation. Of course, that's what we're looking for, and then it gives us a little sigma there. And this summation, we're allowed to put any letter for an index that we want. And so I'm going to put the letter I. I'm just going to make it match perfectly what we have there. I actually want alpha. I hope it didn't just alpha lock, but I want the letter I. I goes from 5 to 9, and our sequence goes 11. And it's going to add up to 55. So there you go. Now what about that one before? Maybe just check the math on this. I'm going to go second entry just to summon this back up. I'm going to leave it as I instead of changing it to k. It doesn't matter. I go I equals 1 to 5. I just have to make sure that right over here, when I call this, instead of k times k plus 4, I need to call it I times, I'm going to close that one out, I times I plus 4. And now see, this sequence with i's is exactly the same as this sequence with k's. Makes no difference. It's going to be the same series as well, same sum, 115. Very helpful. And I hope that that can save you a little bit of time when you do this one. And then we have a sum right here where it's already written out as a sum, and we want to think the other way. Be a little bit creative, try to figure out which sum this is using summation notation. Something we can tell about this, which really what we want to put here is just whatever sequence this is, like an AK. We need to describe that sequence, and AK apparently it's 2, every time it's 2, 2, 2, 2, 2, 2, and then it's just being raised to different powers. This one's to the first power, it's just not written there. So the powers are what are going 1, 2, 3, up to 11. So it's going 2 to the k power. That's what we want. It's going to go 2 to the k power. K is going from 1 up to 11. And so we have this sum, and that's the one which is there. And these are the same. And then we've got another one. I'd like to use summation notation for this. Oh, I see now I was supposed to use I for the index, but let's do it this time. I'm going to call this one BI. BI is this general term, so B1 is 1/2. B2 is 2/3. That's B2. This was B1. And so what in the world is BI? Apparently the top is just counting up. You see how it's just going 1, 2, 3, up to 14. And so let me move my BI, get it away from those. BI is going just I on top, because this index, when the index counts up 1 to 14, this is just going, the numerator's 1 to 14. And then we can divide it by, wow, it gives us so much of a hint on the end that it's just 14 plus 1 on bottom. Even if it were a 15 there, you could see that what the denominator is doing, it's always just one more than the numerator. It's 1 compared to 2, 2 compared to 3. So the bottom's just counting up 2, 3, 4, up to 15. So it's always one more than the top. I plus 1. We're adding this one up, so we're going to go add up the i's from 1. The last one is 14, so I'm going to go up to 14 of I over I plus 1. And it's, to be honest, a little bit rare to use I as the index, even though index starts with the letter I, because a lot of applications where we end up using summation, we are liable to be using complex numbers as well that have the imaginary number I. So we don't want I to stand for the index. We'd like to make I stand for the square root of -1. But here it's just the index. K cleans it up a little bit if we use K instead of I, or we can use M or N or whatever letter you like, maybe the first letter of your first name or last name, and it's all the same. But that's the end of 8.1. We just barely scratched the surface on sequences and series. It's such a rich topic that you can learn lots more about in other math classes. Pre-calculus, it will develop on this idea. Also in calculus, you'll use it. It is a very fundamental idea for calculus. And so I hope this video was helpful to you, and I'll catch you in the next one. Thanks.